Welcome everyone to this ninth video in the STEM-part series on convective wildfires. My name is Tess, and in the past videos we have been discussing how to predict the type of plume, whether or not we get pyrocloud formation among others based on QTs. We have also connected the different types of plumes that we observe in the field to the associated fire behavior. But one of the remaining questions is, how well are the predictions that we make? To check our predictions, we can make use of soundings. In other words, very small balloons that are coupled with a measurement device that measures temperature, relative humidity, and the vertical displacement. And we can launch these soundings either inside plumes to measure the temperature and relative humidity inside the convective plumes. And we can launch these balloons also in the environment in which the plumes develop. Both of them provide us useful insight into whether our predictions are correct or not. However, a main challenge with these soundings is that their data is often represented in terms of conserved variables. And so in this video, I will take you along with what conserved variables are and why they're so easy to use, even though they sound a bit complex maybe. And then in the next video, the last video of this series, we'll have a look at how we can use the sounding measurements to determine how good our predictions are and whether we should adjust our predictions. So first conserved variable that I want to discuss with you is the potential temperature. It's basically a variant on the normal temperature. So let's start there. If we think of the normal temperature and we think of the vertical structure that we have seen in the previous videos that the atmosphere is layered, starting with the convective boundary layer that is capped by an inversion where the temperature rises slightly, and then the free troposphere again. Here free again referring to the fact that the free troposphere is not directly influenced by the land surface, whereas the convective boundary layer is. Here we have this constant mixing of warm air parcels that move upwards, while colder air parcels move downwards. And we know that in this convective boundary layer, when these air parcels rise, they cool down, and when they descend, they warm. If we only consider these two processes, then that is what we call adiabatic rise of parcels. That is generally what we assume is true for the convective boundary layer, that parcels only cool when rising and only warm when due to descending. And with this adiabatic rise, we get a temperature gradient of approximately minus 9.6 degrees Celsius per kilometer altitude. And this value might seem a bit arbitrary, but you have seen it before, because this is the value of the dry adiabatic lapse rate, the line that you have been using in this QTs to determine the boundary layer height in videos 4 to 7 with Brian Verhoeven. And an important note here is that the convective boundary layer, because of this constant rising and descending of parcels, fits this 9.6 degrees per kilometer very nicely. Whereas in the free troposphere, we don't have this constant mixing of parcels going up and down. So here it does cool with height typically, but the rate is not so fixed as we find in the convective boundary layer. So this is the picture that we draw when we think of temperature and the evolution of temperature over altitude, right? Let's now have a look at what potential temperature is. Potential temperature is basically the temperature of any air parcel when we move it adiabatically, so with the dry adiabatic lapse rate towards the surface. In other words, it's the potential temperature of that an air parcel could have when it's moved towards the surface, using this dry adiabatic lapse rate of minus 9.6 degrees Celsius per kilometer. So what does that mean for the potential temperature profile that we would get if we translate our standard temperature profile here on the left towards a potential temperature profile? And the reason we do this, by the way, is because now we get one reference height, the surface. If we translate all temperatures to a surface temperature, we can much easier compare them with each other. And in the next slides, I will show you how. But now let's first try to deduct the vertical profile of the potential temperature. So at the surface, the temperature will be the potential temperature because it's already at the surface. We don't have to move it. Higher up in the convective boundary layer, we have to find the potential temperature, we have to go down with the dry adiabatic lapse rate towards the surface, so using this 9.6 degrees Celsius per kilometer. But in the convective boundary layer, the gradient of temperature is exactly this dry adiabatic lapse rate, meaning that in the potential temperature, we get a straight temperature profile in the convective boundary layer. Within the capping inversion, we see a warming, of course, of the temperature, which also means that the potential temperature warms, which we, in idealized profiles, typically resemble as a straight temperature jump, and that is what we see as the inversion in the potential temperature profile. In the free troposphere, we see again, of course, a cooling, but this cooling is less strong than the cooling of the convective boundary layer, and also less strong than the dry adiabatic lapse rate, meaning that from a potential temperature perspective, the potential temperature does rise in the free troposphere. So this is an amazing profile. But I can almost hear you wonder, what can we do with this? Why do we introduce this complexity? The main advantage of adding this complexity is that it's much more easy for us to interpret the vertical profiles. We don't need the skewed lines from the skewed anymore to understand how the atmosphere is structured. So in this case, if we have this, again, this standard daytime profile, in this case with the potential temperature, we can, for example, very easily determine the height of the atmospheric boundary layer. So during daytime, we know that the sun heats up air particles at the surface, right? They become slightly warmer than the environment and they start to rise. That's why they mix. And if we do the same experiment theoretically to determine the boundary layer height, and we take a slightly warmer air parcel than the environment around it, then instead of having to follow tilted lines, like in the QT, with the potential temperature, we know that every temperature above it is already comparable to the surface temperature. So we can directly move upwards till we reach the point where the parcel becomes as warm as the environment, which is at the inversion. Because if we imagine a parcel rising any further, so any further than this level, and it rises beyond that, it becomes colder than the environment. So in this case, we know that parcels can rise freely up to here, and that is thus the top of the convective boundary layer. So this is determining the boundary layer height, but we can do the same for fires. We know for fires that they elevate the temperature by a certain amount. We have seen in the explanation from Brian Verhoeven that this can vary depending on the size and the nature of the fire. But let's imagine in this case that our fire heats up the temperature up to this point. In this case, that means that we can rise straight upwards and find the height to which the plume can rise freely without getting into an environment where it becomes colder than the environment, right? Because if it rises any further, we are again in a place where I'm colder as an air parcel than my environment, the blue line here. So we know that the plume top is here. And you can already see this is much more straightforward than using the skewed lines from a skewed T. The main reason why we introduced the skewed T first is because the skewed T is a standard output from the meteorological surfaces, such as ECWMF or GFS. They do often not provide these kinds of conserved variables like the potential temperature. But our soundings do. They directly show it in the software. That also means that you can directly see how high your boundary layer height is and how high your plume can develop. A remaining question, of course, is now we have seen the potential temperature, but what about moisture? When we talk about moisture, we often talk about the relative humidity, as that is the saturation value for air with regards to water. So if the relative humidity is 100%, we get the formation of clouds. And there's nothing wrong with the concept or the value of relative humidity. But what is sometimes challenging is the fact that it's dependent on the temperature, which varies with height. So the relative humidity will also vary with height. A solution to this is the specific humidity, which is a conserved variable that expresses the amount of water vapor per amount of air, often expressed as the kilograms of water vapor per kilograms of air. And as you can hear from the definition, this is completely independent of temperature, because temperature does not influence the amount of kilograms of air, neither does it influence the amount of kilograms of water vapor. So how would it look like in a stereotypical daytime boundary layer profile? If we take a standard profile and we define somewhere a boundary layer height, we know that within this atmospheric boundary layer, this convective boundary layer as it is during daytime, we have constantly convective parcels going up and then other parcels going down, constantly mixing the whole atmospheric boundary layer. And this means that the water vapor is very nicely equally distributed throughout the domain, resulting in a straight line within the atmospheric boundary layer, basically meaning that the specific humidity is constant over altitude. Above the atmospheric boundary layer, we typically see a drying with over height. So the free troposphere is typically drier than the atmospheric boundary layer. And it's very intuitive to understand why, because the main source of moisture for the atmosphere is the transpiration and the evapotranspiration that happens at the surface. So when the surface is the only source of moisture, and this is transported upwards by the convective parcels, but the convective parcels only reach till the top of the atmospheric boundary layer, but not above. So the atmospheric boundary layer is typically moister than the air above it, so the free troposphere. So to summarize what we have discussed today, we have two types of conserved variables that the soundings show. The first is the potential temperature, which has a mixed layer, a positive temperature increase, and then it warms in the free troposphere. Additionally, we have the specific humidity, which is the amount of water vapor per amount of air, which is nicely mixed within the convective boundary layer, and then above the boundary layer, we typically have a much drier free troposphere because the main source of humidity and moisture is the Earth's surface. I realize that it's more complex, but I hope I've been able to show that it's much easier to distinguish the atmospheric boundary layer and the potential plume height than using skewed T's. In the next video, we will see how we can use knowledge from these sounding measurements directly in operation. So how can we detect at that moment how well our prediction is actually being compared to the measurements that we do in the field. Thank you very much for watching and hope to see you in the next video.